In progress.
Okay, welcome back to day 2 of AFRICAST, everyone. Great to see you have decided to join again for the second day. Today, you've got me for the entire day. I believe Bahman might be joining here and there. Not sure if you're here, Bahman. Yes, you are. So Bahman will also be here to help answer the questions that you'll put in the chat throughout the day. Today is all about, again, exploring the patterns and understanding how to describe the patterns that exist in a time series so that tomorrow even, we can specify some suitable models and calculate some appropriate forecasts for the time series patterns that we observe. In particular, we're going to look at decomposition of a time series, which is a method of splitting apart the patterns into their components. So we'll take a single time series and extract the trend, seasonality, and whatever is left over, which we call the remainder. And we'll also be looking at those terms separately. So there's a few mathematical tricks that we'll need to use in order to use a decomposition technique. But decomposition is a powerful tool for not only looking at the patterns more clearly without the other trend getting in the way when you're looking at seasonality, for instance, but it's also useful for summarizing the patterns in many time series. So we'll also be using decomposition to summarize how strong the trend and seasonality is, allowing us to summarize the behavior of hundreds or thousands of time series in a single graphic. So I'm just going to switch over to the AFRICAST website again. Give me a moment while I share the screen. Okay, so once again, hopefully you have access to the website here. I do now have access to the chat, so I can see the questions that you're asking. So I'll pop that in the chat as well. And for today, we're going to go to the schedule. And we're going to start with the day 2 exercises on transforming and adjusting time series. So I'll put the direct link to this as well. So hopefully you can get access to these slides and follow along as I go through them. Okay, I've just seen a message in the chat that the shared screen is not very clear. It's still loading for me. Okay, here it is. Is everyone able to see this screen in high resolution?
Yeah, it's very clear.
So maybe it's just your internet connection, Milo. So hopefully that improves shortly. Okay, so there's a few things for us to look at for decomposing time series. Before we're able to decompose time series, we've got to learn about how we can transform a time series, because these transformations are necessary to handle some multiplicative patterns that we talked about yesterday. So the main type of mathematical transformation that we need to use in order to decompose our data is to stabilize the variance. And when I talk about stabilizing the variance, this is very similar to when we looked at the multiplicative seasonal pattern. Let me draw that for you. We saw this yesterday. Remember when we had a time series that looked a little bit like this with a multiplicative seasonal pattern? And I talked about how there was a cone shape for the seasonal pattern. That's how we could identify if it was multiplicative or additive. An additive one had a constant variance, meaning these orange lines that I'm indicating the variability was always the same. But for the time series that I've just drawn, at the start of the data, the variation is quite small. And at the end of the data, the variance is much larger. You can see how much it's varying towards the end of the data compared to the start. Now, this poses a problem for our decomposition methods. In particular, the method that we'll be looking at today, SDL decomposition, only works for additive time series. So if your data looks like the one that I've drawn, where you have this cone shape of increasing or decreasing variance, it's not possible to at least directly use that type of decomposition. Instead, what we need is a time series that looks closer to this. The same constant variance, regardless of where we are in both time and the level of the series. So no matter where we are on this y-axis, the variation is always the same. So our goal for today, to start this session, is to learn how to convert a multiplicative seasonal pattern into an additive seasonal pattern using some sort of mathematical transformation. And that will allow us to decompose the patterns of trend and seasonality more easily. So there's a few different types of transformations, mathematical functions that we can use for this. And these vary. The ones shown here are some common ones that we like to use, and they vary in how strong the transformation is. So a square root transformation is one of the weaker transformations for stabilizing the variance. It will make bigger variance for large values smaller. So when the level of the series is large, let's draw that again. A square root transformation, and in fact both a cubed root and a logarithm, will all act to make this variance smaller and this variance bigger. So the idea is that by choosing the appropriate transformation with the appropriate strength, we will be able to get the same variance across the entire time series. This will be easier to see once we look at an example. So here's a time series that we can try out in R. So I'm going to open this one up in our project for AFRICAST. So I encourage you to try to follow along with this one. So open up RStudio, and I'm going to create a new script for day 2. Now, at the start of each script, we'll need to load in the FPP3 package. Just like we did yesterday, this will include all of the data sets and all of the functions for plotting and modeling, forecasting the data that we'll need this week. So you should get a message saying all of the packages that have been loaded with FPP3, and that should allow you to run the next line of code. So I'll put this in the chat as well. Now, last week we learned how to do a time plot using the autoplot function. And we also learned how to explore and filter a time series. So perhaps as a recap of yesterday, a very quick recap, starting with a data set called Oz Retail. This is a fairly big data set with 64,000 rows and 5 different columns. Now that I can see the chat, perhaps this is a good question, time to ask some questions. What are the key variables of this time series? That's right. So you can read the key variables from the output of a Sybil. So perhaps I should have hidden that. When I loaded in the data set from a CSV file or from a database, it looked like this. So it's not going to tell you what the answer is. But you're right that the key variables are state and industry. They're 2 character variables. Now, you could also say that series ID is a key variable as well. This is a character variable, and you would be perfectly correct to say series ID is a key variable. The reason why this data set doesn't include series ID as one of the key variables, see how we've only used state and industry, is because this is redundant and meaningless. This is our government's way, the Australian government, the Bureau of Statistics has these IDs, unique identifiers for each time series. So this is useful to understand where the data is coming from, and it can act as a unique identifier for each series as a key variable. But for our purposes, it's better to use descriptive variables if possible, so that we can do things such as filtering only the food retailing industry. If we use series ID as our only key variable, then it will be not as easy to manipulate and visualize this time series. I will still have access to these ones, but the automatic displays of key variables in the plots will instead show this number or this text instead of the more intuitive state and industry. Okay, it looks like there's some issues with the screen sharing. I'm going to reshare for everybody. Hopefully change the settings to make that a bit. Does it say that it's not recording? It looks to me like the meeting is being recorded, so that shouldn't be an issue. Fantastic. Thank you, Bahman. Okay, very good. I think everything's working again. So back to where we were. The key variables for this time series are state and industry, and the index variable for this time series, the time index, the time column, is month. So the measured variable that we're interested in forecasting is turnover. So also what we did yesterday is learn how to calculate a total. So we use the summarize function to add up all of the different values for food retailing. There's 8 different time series of different locations around Australia. And by using the summarize function, we're computing the total. We're adding up the total turnover for each state. And the result is a single time series that I've called food with this assignment operator. We call this the gets operator. So I've saved my resulting data set as food, and we'll be looking at this quite a bit for decomposing the patterns. So you can see now the food data set doesn't have any key variables. We've combined all of the information across all the states, and we're focusing only on the food retailing industry. And when I plot the data, you can see on the right is how the data looks in a time plot. So I want to also test you on yesterday's skills. What patterns can you see in this time series? Remember, we had patterns such as trend, seasonality, outliers, perhaps cycles could show up in this data set. What patterns can we see in this plot? Fantastic. So everyone's picked up on the trend. And everyone seems to be saying seasonality, and a few people are also saying multiplicative seasonality, and that's exactly right. So I don't see much cycles or any unusual observations in this data set, at least not from this plot. But the main feature that I can see is an increasing trend. And I can also see a seasonal pattern. See how it's repeating of the same shape every year? We've got these peaks that seem to be in December. So a lot of people eat lots of food around the holiday season, or at least buy a lot of food for Christmas and the holidays. And that variation seems to be getting stronger and stronger as turnover increases. See, at the start of the time series, when turnover was fairly small, we have a fairly small seasonal variation. However, in the recent years, when turnover is much larger, you can see the seasonal pattern has much larger variation. So before we're able to model this time series and decompose its patterns of trend and seasonality to see them separately, we will need to transform the data. The goal here is to make the seasonal variation, this part, this small variation, and this big variation, we want that to look roughly the same size. And we're going to do that with a square root, a cubed root, which we can write with y to the power of -3, or a log transformation. There are three common ways, simple ways that we can use to simplify the patterns in the data. So let's start with one of the weakest transformations, which is a square root transformation. And you can see in the autoplot function, I'm telling it what variable I want to plot. So here I'm trying to plot turnover. What I can also do is transform the data. So I can use a square root transformation of turnover and plot that instead. There we go. Hopefully I can compare the pair. So let me go back and forth between these. Here's the original plot. Have a look how small the data was at the start and how big it was at the end. Now when I switch to the recent plot with the square root transformation, you can see this data is getting stretched out, or at least it looks like that, and the variability at the top is much smaller. Now, would you call this a multiplicative seasonal pattern or an additive seasonal pattern after I've made that change? Very good. So I'm seeing everyone say multiplicative. Yes, this still looks multiplicative because our variation at the start is still smaller than our variation at the end. So then we need to try something a bit stronger. So let's try a cubed root transformation. So I can take turnover and raise it to the power of a third. I'll put this code in the chat as well, so you can try this out. So now we've done a cubed root transformation. Is this good enough? Do we have an additive or a multiplicative time series? If it's still not good enough, we'll need to try a log transformation. Okay, I'm not seeing as much activity in the chat here, so this one's a little bit less clear. Is this one additive or multiplicative? A couple of people saying multiplicative. I'm going to wait for a few more attempts. Multiplicative. Yep, everyone seems to think this is multiplicative, so let's try going one step further, and we'll do the strongest transformation that we've seen on the slide, a log transformation. And what about now? Is the variability at the start of the time series and the end of the time series the same? We want it to have the same variability throughout the entire time series. Very good. So everyone's saying additive now? So a log transformation is what we need to do in order to stabilize the variance. And if you think about trying to predict this pattern into the future, this is going to be much easier to forecast going into the future. Because rather than predicting how much, let's go back to the original one. If you tried to draw a forecast from this plot, you would have to guess how much bigger the seasonal pattern will get in each time point. And applying this multiplicative growth is pretty difficult. However, if I can simplify the patterns using a transformation such as a log, now it's going to be much easier because I can simply copy the same variation in the seasonal pattern for the future. It's much easier to predict what the shape will be in the future. So applying a transformation to stabilize the variance is good practice to simplify your model. And it will often give you better results for your forecasts as well. But for some models, they only work with additive patterns. So this technique of using a log transformation or something else is really important in order to find in order to use some models that only work with additive patterns, such as a regression model. Okay, so here's the slides for that. You can see a multiplicative pattern for the original data. When I compute a square root transformation, it looks a little bit better, but not good enough. The root transformation is again an improvement, but it's not strong enough. And once we do the log transformation, it looks pretty good. But there's a statement in the chat, which is very relevant. It seems to change the trend as well. You can see the trend in the original data sort of curves upwards like this. Oops. However, as I apply a stronger and stronger transformation, you can see now the trend looks fairly linear. The log transformation has started it curving the other way. Let me draw that again. You can see how the trend has changed. Now, ideally, we would have a trend and seasonality which are both additive, meaning that the trend, will look like this, a straight line, which is very simple to forecast. And the seasonality will look like this, where it's a constant variation through the entire time series. Now, that's not always possible. So if we have to make a choice for what one we want to be easier for forecasting, we prefer to have the seasonality having constant variance, and it's okay if the trend has a slight curve to it. Now, I can also do a stronger transformation than a log. This is raising turnover to the power of -1, and we're showing the negative of turnover. And in this case, we've got the opposite problem. When the level of the time series is small, the variance is large. And when the level of the time series is big, the variation is small. If you see something like this, it suggests that your transformation is now too strong. So you need to use something weaker, which is closer to perhaps a square root transformation. The idea is to try different transformations and find the one that gives you the simplest patterns, especially for seasonality. There's a question in chat. So the log turnover reduces the noise. The log transformation can help to stabilize the variance. And what that means is that if you've got different amount of variation, so small variation and large variation, for different values different levels of the time series. Level means the height, how big the values are. Then using a log transformation or a square root or one of these power family transformations will help simplify the patterns by making the variation consistent. So for this time series, the best transformation is something like a log transformation. You can see log here is getting consistent variation for the entire time series. So generalizing this, there's actually a whole family of transformations that we can use. And this is called a Box-Cox transformation. Before I get to this, there's a question asking about the inverse transformation. So the inverse transformation is even stronger than a log. So we could go, let's switch back to R. We could do a identity transformation. Which is essentially doing nothing, right? We're just plotting the original data. We could do a square root transformation, which is going to scale the variance a little bit. We could do a cubed root transformation. And this is going to scale the variation even more. But if we look at this data, it still looks multiplicative. So we need to do an even stronger transformation. So we might try a log transformation. And that appears to have made the seasonal variation consistent. If I went one step further and did an even stronger transformation, we could do an inverse transformation. So just like a square root, a cubed root, a log transformation, an inverse, these are all in increasing order of strength. So starting with identity, its stronger transformation is a square root transformation. And then a cubed root transformation is even stronger than this. Let me use the code for this. A square root transformation, a cubed root transformation is even stronger. And then lastly, an inverse transformation, a log transformation is even stronger than that. And then lastly, an inverse transformation is about the strongest that you would ever need to consider doing. There are stronger transformations than this, but we never have to use them in practice. So an inverse transformation is just another type of power transformation, which is, in this case, way too strong, because you can see that the variation is now different for different levels of the time series. We've got the opposite problem that we had before. Now the variation at the start of the time series, when the values are low, is very big, and the variation at the end of the time series, when the values are big, is a very small variation. So that says to us that we've gone too far with our transformations because we've now got the opposite problem from when we started. When we started, the variation was small when the values were small, and the variation was big when the values were big. So the idea is that we want to find a transformation such as the log transformation for this data set, but it will be different for every data set. We want to find a transformation where the variance is the same for small values and also for big values. There's another great question. Why do we use the negative in the inverse transformation? This is just to keep the trend looking the same way. So if I did an inverse transformation, you can see the trend is now going the opposite direction and it gets a bit confusing. If I did a negative value in front, now it follows the same appearance as the trend for all other transformations as well. So when you need to do something stronger than a log transformation, we need to put a negative in front. The same applies for if we're doing a negative turnover squared transformation. This one is even stronger than just an inverse transformation. Okay, any questions on these transformations? Perfect. Okay, continuing on. We have another set of transformations which combines all of these transformations we've seen so far. And this family is called a Box-Cox transformation. And you can see the way it works is that if lambda is equal to 0, that's a special case, we get a log transformation. So that only happens when lambda is equal to 0. Except for every other transformation, when lambda is not equal to 0, so let's imagine what happens when lambda is equal to a half, then we'll have y to the power of a half minus 1 divided by a half. What this essentially does, when lambda is equal to a half, it's roughly equivalent to saying the square root of y. When lambda is equal to a third, it's the same as a cubed root. Because you can see the main change in this equation will be y to the power of lambda, which will now be y to the power of a third. All of the other parts here, this -1, this lambda, the sign, these are just to make it appear as a continuous function. So as you adjust lambda in very small increments, it's doing very small changes. So in fact, all of these transformations that we've seen so far have an equivalent lambda value. The identity transformation, when we do nothing, is equivalent to lambda equal to 1. The square root transformation is when we have lambda equal to a half. The cubed root transformation isn't written here, but that's when we have lambda equal to 1/3. Lambda equals 0 will be the log. That's the special case that we see in the first row. And lastly, lambda can go negative as well. So we can do lambda equals -1, which will give us the inverse transformation. Lambda equals -2 will be inverse y to the power of 2. There's a question, can lambda be greater than 1? Yes, it can. So this is equivalent to, say, y squared transformation, rather than the square root of y. The opposite also applies when lambda is greater than 1. So this lambda value is a parameter that allows us to control the strength of the transformation. Usually lambda will be between 0 and 1. And a value further away from 1 is a stronger transformation. So lambda equals 0 is usually the strongest transformation that we would use. However, it is possible for lambda to be less than 0 and greater than 1 as well. So perhaps we could see lambda with an example. I'll show you this animation later, but let's switch back over to R. And I want you to try using a new function, Box-Cox, of turnover, and then choose different numbers for lambda. So I'll put this into the chat so that you can try it for yourself. If I try lambda equals to 0, this is equivalent to the log transformation that we chose earlier as being the best one. Can you do any better? We could choose lambda equal to 0.1. And we get a slightly different result. We could choose lambda equals to -0.5. Lambda can be any number, but it's usually between 0 and 1. You can see lambda can go larger than 1 as well. And that really makes the problem worse. So now my values are even smaller when the values are small, and bigger when the values are big. So that goes against our goal of trying to stabilize the variance. So where these mathematical transformations of square root, cubed root, log transformation, inverse are fairly discrete, there's big differences between each transformation, The lambda transformation, the Box-Cox transformation using lambda, can allow you to get a very precise, exact change for the transformation. So perhaps for this time series, 0.1 could be a good value. So there's a question in the chat. When we use lambda equal to 0, is it the same as doing a log transformation? Yes, it's identical to a log transformation. And you can see that in the math here on the first row. When lambda is equal to 0, the resulting transformed data will be exactly equal to the log of the data. So I want you to watch carefully when I play this animation. This is starting with that same data set when lambda equals to 1. But what I'm going to do when I click play is you'll see in the title the lambda value is going to change. It's going to get smaller. And you'll see that the shape of the seasonality will change as well. Well, this might not actually work on this computer. Hold on. I'll show you this from the textbook, actually, because the textbook allows us to do an interactive exploration of it. So I'll give you a link to this as well. We're currently working from chapter 3 of the textbook. So here's where I'm looking. You can see there's a different example here. Using the quarterly gas production in Australia. And currently we're starting with a lambda value of 1. But I want you to see what happens when you drag lambda to be different values. Because we can currently see that this is a multiplicative seasonal pattern, because when the values are small, the variation is small. And the variation is getting bigger for larger values of production. So if I make lambda smaller, I'm going to have a stronger and stronger transformation. And you can see that this is stabilizing the variation of gas production. See, the small seasonal patterns are getting bigger and the big ones are getting smaller. So we want to stop when it looks roughly the same size. You can see now when I'm in the negative lambda values, I've gone too far. You can see I now have the opposite problem when the small seasonal shapes are bigger and the variation at the top is now much smaller. So I need to go closer to 1. You can see now it's improving. The variation is looking more similar. And we need to decide when we should stop. So it seems to be a value of lambda of 0.1 gives us the same variation at the start of the time series as the end of the time series. So this would be a suitable transformation for gas production, lambda of 0.1. One of the great things about the Box-Cox transformation is that it doesn't have to be precise. As long as you're within 0.1 of the actual value, the transformation will be good enough. But an even nicer thing is that there's a trick that we can use in order to calculate the ideal value of lambda completely automatically. And this is called Guerrero's method. So this is named after a guy called Guerrero who invented the technique. And you can calculate Guerrero's statistic, which is the optimal value for lambda, using the features function. So we'll use the features function quite a lot today. We're going to calculate features of the turnover variable, and we're going to compute Guerrero's feature. And what this tells us is that the optimal value for lambda is 0.0895. So very close to the 0.1 value that we were looking at before. So if I use this optimal value, this is the value that produces the most additive, stable variance for the entire time series. So the best value that we can use for this data set is found using Guerrero's method. Now, if you were to use a log transformation instead, that would still be good because 0.08 is very close to just 0. It's within 0.1. And so often we prefer to use a log transformation because it is simpler and has nicer interpretations. A log transformation can be interpreted as percentage changes in the values when you interpret the coefficients, whereas a box-Cox transformation with lambda 0.0895, changes in this is pretty meaningless, but it will produce more accurate forecasts. So depending on what you need, accurate forecasts or interpreting the results is a good way to decide if you're going to use a simple transformation, such as a log transformation, or a box-Cox transformation. Let's have a look at a different example. I have to think of one. So let's try. Maybe we try Oz Retail. That's what we're currently looking at. Let's try PBS.
Yeah. You watch TV. No,
I'll put this put this in the chat box. I want you to replace this value of lambda. Currently it's lambda equals 1. I want you to try different values of lambda to convert this multiplicative time series into an additive one. So you can see the variance is too small here and too big for the larger values. Try playing around with different values of lambda so that you get the same variation for the entire time series. And once you think that you've got a good value for lambda, I want you to put it into the chat. So I expect this will take a little while, but all of the code is there in the chat for you to catch up. All you need to do is try different values of lambda, probably between 0 and 1, but not necessarily. Okay, I see an error that was reported in the chat. If you get this error, could not find function autoplot, let me show you that live. Just need to restart to show you. If you get an error like this, could not find function autoplot, this means that you've forgotten to load in the FFP3 package. So all you need to add to this is the same code that I added right at the top of my script, library FFP3. So the PBS dataset is included in the FPP3 package, and the food dataset also came from the FPP3 package, but we needed to apply some transformations to get it. So that was done right at the top here. I'll put this in the chat for you to catch up. We computed that from the Oz retail dataset, which is included in FPP3 as well. Okay, so to fix this error, you run library FPP3 to load in all of the packages that provide the functions, and then you should be able to produce the plot. Okay, we have one person that has finished the exercise. I'll give you a little bit more time to try out different values of lambda. You can see if I did 0.8 and look closely at the plot on the right, it gets a little bit better. We have one suggestion of using 0.6. So let's have a look. You can see this is much better than where we started, right? The variance at the start is much closer to the variance at the end. But I do think that this looks a little bit bigger at the end than it did at the start. This honestly would probably be good enough for a model to use this data, but I think we can do better than lambda of 0.6. Another suggestion was lambda at 0.5. So this is equivalent to a square root transformation. And this also looks pretty good, maybe a little bit better than the one before. I also see a few people have tried Guerrero's method. But before we get to that, I see another suggestion of 0.25. So this would be a fourth root of the data, raising the y to the power of a quarter. And here I think we've gone a little bit too far. This appears to be too strong. You can see that the variation at the start of the data is now a bit bigger than the variation at the end of the data. So it's going to be bigger than 0.25 and smaller than 0.5, somewhere in between. And there's a question in the chat, can't we just use Guerrero's method? That's exactly right. So let's see what Guerrero's method tells us to see what the correct best transformation is. Guerrero's method doesn't always work, but it's pretty reliable. So instead of doing autoplot, I can instead compute features using Guerrero's feature. And it says that the optimal value is actually 0.364. So if you got within 0.1 of this value, you've done very well. So anywhere between 0.3 and 0.4 would be a very good transformation for this data set. The purpose, again, of doing this transformation is to make it easier to use a model. And some models will only work with additive data. So if you have multiplicative data, you'll first need to convert it into an additive time series using one of these transformations, such as a square root, a log transformation, or more generally, a Box-Cox transformation. So here's some notes to summarize. For transformations, usually you don't need any transformation. It's only if you want to use a model that requires additive time series. In which case, a log transformation or a Box-Cox is good. One of the downsides of using a transformation is that they can result in very large forecast intervals. And we'll see this at the end of the week when we look at producing forecasts. One of the issues is if your data is negative. It's not very common because usually we work with data that is some sort of count. So it's usually all positive values. Then we need to use positive values for lambda as well. However, if you take a log of 0, remember that can cause some issues. Right? What's the log of 0? Negative infinity. So this transformation cannot be used or a log transformation cannot be used if you've got zeros in your data, which is fairly common for specific time series. And so instead, we often use log plus 1. So you can use the log1p function in order to do a log transformation for data that has zeros in it. So that's the main type of transformation that we like to use for time series analysis and forecasting. But there are a few other different types of transformations I'd like to briefly talk about before we start decomposing a time series. Now, imagine the GDP of Australia, right? I think it's 1.5 trillion per year. Now, this is pretty meaningless if I wanted to compare the GDP of Australia with any other country. So it's quite common and quite useful to adjust GDP by population. You might have heard of this before, GDP per capita, because it's a very common type of transformation. Per capita transformations are useful if the variation or if the values vary with the number of people that are in that sample. So Australia, a fairly small country as far as people, will have, as a result of its rich GDP, has a per capita GDP of about 60,000. Doing a per capita adjustment allows us to compare the GDP or the wealth of Australia with every other country. Another type of adjustment that is very common for if you're working with financial data is to adjust for inflation. So you might have heard that inflation is out of control at the moment. The prices of things at the supermarkets are getting more expensive. So it's useful to consider the income or the turnover or any monetary values in terms of real changes, rather than changes just attributable to inflation. And this can be done by dividing the financial variable that we're interested in this case turnover, dividing that by some indicator of inflation, such as the Consumer Price Index, CPI. All of the code here looks pretty intimidating, but it's essentially joining in the CPI data from the global economy data set with the turnover data from the Oz retail data. So it's a little bit more complicated because we're joining in data sets from two different places. And you can see that this has a pretty big change in the interpretations of your data. Previously, this is the original data. Oops. The original data turnover appears to have had an increasing trend for almost all of the time series. Until 2010, then the trend has started to decrease. But if I instead look at adjusted turnover, which accounts for inflation, you can see that we've actually had, in real dollar terms, a decrease for the entire time series. And it recently has gotten even stronger. So it's not looking good for the newspapers in Australia. They're becoming less and less relevant because, of course, people are using the internet to get their news now. So these sorts of transformations, per capita adjustments and inflation adjustments, are useful to understand the actual changes in behavior or the strength of an industry, rather than just looking at the raw numbers. So if you wanted to learn a little bit more about adjusting time series, there's a lot more information in the textbook in that chapter that I sent you. So you can also adjust for calendar effects. Some days have more days than others. Population adjustments that we saw with GDP per capita. Inflation adjustments for whenever you're working with monetary terms. But for this week, and for almost all forecasting that I do, we focus on the mathematical transformations of the box, cox, and log that we started with. These are the most useful transformations when it comes to forecasting. So again, you can find more information in the textbook at this link. There's another question, can I get a PDF version of the textbook? No, there's only the web version of the textbook and a print version of the textbook. So the closest that you'd get to a PDF is the print version in physical form. Other than that, it's only available online for free. Okay, on to the next topic of time series decomposition. This is a very powerful technique for just about everything in time series. It's useful for you to better understand the patterns in the data, to visualize the patterns in the data, but it's also a useful forecasting technique as well. And it'll be the main topic that we look at today. So time series decomposition is the idea of splitting up a time series, such as YT, into individual patterns of seasonality, trend, and everything else, which we call the remainder. And there's many different types of decompositions that you could use. We're going to focus on one type of decomposition known as an additive decomposition. Because the model that we'll use, called an STL model, only works for additive decompositions. It uses something called LOS. You might have heard of this if you have worked with regression before. LOS stands for localized regression. And if you remember, a regression is an additive model. And so that's why this model only works for additive time series. But fortunately, we know how to get a multiplicative pattern converted into an additive pattern. And we do this using a log transformation or a box-cox transformation that we'd just seen. There's many reasons for why we like to use an STL decomposition. They're all listed here. The main reason is that it's very flexible. It works for many different types of seasonality that we saw yesterday, including multiple seasonal patterns, such as what we saw in Victorian electricity, where we had both a daily seasonal pattern, when people use less electricity when they're sleeping, a weekly seasonal pattern, where people use less electricity on weekends, and finally, it also works with annual seasonal patterns for the overall effects of electricity demand as the seasons change for the winter and summer, when people use more electricity, and also autumn and spring when it's much more comfortable and people use less electricity. Another nice thing about the STL decomposition is that you can control how it gets the trend and seasonality out from the data. In particular, we adjust the seasonal window and the trend window to control how smooth the trend and seasonality changes over time. So I'll walk you through an example from the slides, and then I'll work with you in R to see how we would decompose the data set that we're looking at before. So here's a new data set. This one's US employment in retail trade. I think we might have seen this one yesterday. But in this case, it is already an additive time series. We can see that it's additive because the variation for low values of the time series is similar to the variation of higher values in the time series. So this time series can immediately be used with an STL decomposition without any transformation needed. The way we do an STL decomposition is using the model function. So you take your time series, the Sybil that we learned about yesterday, and we pipe that into the model function, and then we choose the model that we want to use. In this case, it's an STL model on the employed variable. So very similar to when we used autoplot of the employed variable or autoplot of turnover. In this case, we're using an STL decomposition on employment. And this is the same way in which we'll estimate models for forecasting tomorrow as well. After we estimate our model, we can extract the components from that model. In particular, the Y value is equal to trend plus seasonality plus remainder, just like we saw in the mathematics earlier, using the components function. And components will give us a table, a decomposition table. It works very similar to a Sybil, but it understands the relationship between these variables, that employment is equal to the trend plus seasonality plus remainder. There's a question in the chat, when do we need to decompose the data? Decomposition is a useful technique for understanding the patterns in the data. So yesterday we saw how to visualize the data using a time plot and seasonal plots to look at the trend and the seasonality. However, when we looked at the seasonal pattern, it was pretty hard to see because the trend was in the way. Using a decomposition allows us to separate the trend and seasonality to see them more clearly on their own. It's also useful for forecasting, which we'll see in a future day. Now, this decomposition function also has an autoplot method so that you can see each of the components separately. In the first plot, we see the original data, which has the trend, seasonality, and remainder all mixed in together. But below it, you can see each of the components of trend, seasonality, and remainder have been plotted separately. So now it's a lot easier for us to see the underlying trend, the shape of the seasonality, and the random effects, such as outliers, that would show up in the remainder. This is also the plot that we'll be using to identify the appropriate parameters for the model. How do we choose the windows that say how smooth the trend and seasonality should be? We'll see that with some examples later. Another useful way of visualizing a decomposition is to plot it on top of the original data. So to evaluate how well the trend, it's shown in orange, matches the trend in the original data, we can plot the original data in gray. You can see I'm using autoplot here, but I've set the color to be gray, giving me that gray background, or the gray line in the background of the original data. And then I've added on a layer. This is a new function for us called auto layer. It works just like autoplot. We give it the data set first, and then the variable that we want to plot, in this case, trend. And I've given this a nice orange color so that we can see that the trend follows through the center of the data the way that we would hope it would. So this is a very useful type of plot to include in a report when the seasonality is not so interesting for decision-making. It's really the long-term change in the trend, which is more important. Also notice that when we say trend here, what we're actually saying is trend cycle. You can see the business cycle that we talked about yesterday, this increase, decrease, increase, global financial crash, decrease, increasing, and then probably soon we'll have another crash. Or in fact, it did crash for COVID-19 just at the end of this data. So this business cycle is also included in the trend component. Even though it's just called trend, it is the trend and the cycle combined. Now, the autoplot isn't the only type of plot that we used. Remember yesterday we also saw seasonal plots and seasonal subseries plots. A decomposition makes it much, much easier to see the shape of the seasonality because we're no longer looking at the trend. So it's very common to take the components of a decomposition and then use GG subseries or GG season to visualize the seasonal pattern. And in this case, while it looked like the seasonality was fairly consistent, we can actually see the September employment was decreasing, December employment was decreasing, while April and perhaps May employment is increasing. So there's a very slight change in the shape of the seasonality over time. If I didn't do a decomposition for this plot, let me show you what that would look like. Don't worry about trying to copy this code down because I'll give you a different example to work on next. If I didn't decompose this data set and we just look at plotting the data, which is employed, and then I did a GG subseries of this variable, you can see that all of the subseries really look the same, right? They've got this sharp increase at the start, and then it's fairly flat with a bit of a drop and increase, right? Every subseries looks the same because what we're actually seeing here is the trend. The trend is making it difficult for us to visualize changes in the seasonal pattern. So if we instead do an STL decomposition, extract the components from that model, so now we've got a time series that has just seasonality on its own, season year. And now I'm plotting only the seasonal component without the trend, without all of the random noise. I get a much cleaner view. Oops, something's not working here. Let's try that again. I've never seen that error message before, so I don't know what's going on there. There we go. Seems temporary. Now I don't have the trend to worry about when I'm plotting my seasonality. So I can much more easily see the changes between each month. I could also look at a season plot for this. So just looking at the shape of seasonality for the employed variable, you can see that all of these lines are really spread out. And the reason why they're so spread out is because of the trend. The trend is making it much harder for me to compare the shape of the seasonality between each year. If I instead did a season plot of only the seasonal component, I no longer have that trend in the way. And you can see I get a much more clear visualization of the shape of the seasonality. And we can see the drop in September. We can see that the minimum is February. And at the start of the time series, it used to be March, but now it is in now it's in February, the minimum. And the maximum is very obviously December. Using seasonal plots and seasonal subseries plots of just the seasonal component is much easier to see the shape of the seasonality if I flip between these two. So that's one of the main reasons why I would use a decomposition, to make it easier to look at the seasonal pattern. It's also very commonly used to only look at the trend, which is useful for decision making. Often you'll see your statistics office report seasonally adjusted data. That essentially means we have removed the seasonality from the model, from the data. And for an additive decomposition, this can be done simply by subtracting the seasonal component from your original data. For the multiplicative decomposition, we also just divide. Now, this is a very similar plot to what we showed before with the trend, but the seasonal adjust column, season adjust, automatically does the appropriate transformation to remove seasonality from the model. And you can see now the trend line has a few bumps in it. Those bumps correspond to the random noise, the remainder term. Everything that isn't trend or seasonality has been added and included in this plot as well. So this is a useful way of including some confidence in how smooth the pattern is in the data. So very commonly, seasonal adjusted data is used for visualizing trends and cycles because it includes any outliers or anomalous behaviors. And looking at just the seasonality on its own is useful to look at the seasonal pattern. Okay, I'm going to skip a little bit here because this is talking about choosing different windows for the seasonality. And I'd prefer to show you this. Okay, very good. So I'm going to try this with the Oz retail dataset. In fact, the food retail dataset that we prepared earlier. Now, the food dataset is multiplicative, and we previously saw that the best transformation was a box Cox with lambda equals 0.895. I'm just going to use a log transformation because it's simpler. So step one of doing a decomposition is to transform the data if it is multiplicative. Because remember, an STL decomposition only works with additive data. Step two is to perform the STL decomposition. So we do this with the dataset, model, and then we specify that we're going to use an STL model on the log of turnover. This is where we put in the transformation that we found in step one. And then I get a model like this. Now, to obtain the decomposition, I use the components function. So now I've separated log of turnover into trend, seasonality, and remainder, these columns next to it. And I'm going to save this for later because I'm going to use it a few times. I'll call it food decomposition. And then step three is to plot the decomposition, which we can do with the autoplot function that we saw yesterday. Remember, autoplot's very clever. It will understand the type of data that you're plotting and produce the suitable plot for it. So time series data will give you a time plot. ACF will give you an ACF plot. And decompositions will give you a decomposition plot. Now, step four is sort of going back to step two. We need to adjust the decomposition. Usually the defaults are pretty good, but this is where we can improve the decomposition by adjusting how smooth the trend and seasonal components are. And we do this with something called windows. So let me get some more space for this. The way we specify the window size for trend and seasonality is using the tilde. So you might have seen this in the lm function before. Everything on the left of tilde is my response variable. So in this case, I'm forecasting the log, or I'm decomposing the log of turnover. And everything on the right is exactly how I'm going to decompose the data. So I'll put this in the chat. Now, these windows have to be whole numbers, right? So let's see what happens. The default is 13 for seasonality, and it's usually pretty good. But let's see what happens when you choose different values for the window, for the trend. So when I choose a window of 1, I'm essentially cutting the data set up into sizes of length 1. And then I'm fitting a regression model on each of these windows and estimating the trend. So with a very small window like 1, you can see my trend is now very, very flexible. So flexible, in fact, that it's including all of the random variation, which should be in the remainder. Now, some people think when I get remainder of 0, I've got no errors, I'm doing very well. That's not the point of a decomposition. In fact, this is overfitting the model, and it's something that we want to avoid. We want the trend to smoothly follow the center of the data in the original. So in this case, the window for trend is too small. We need to increase it so that it's smoother. Let's go to the other extreme. What if I made the window very, very big? Now I only have a single window that contains the data. So I've got my localized regression for the trend is just a single model for all of the data, and it's a linear model, so I get a straight line for the trend. That's as smooth as it could possibly be. Now this is also bad because it's too smooth. You can see that there was a few bumps along the way in the data that my trend is no longer able to capture, and so those changes are showing up in the remainder. My remainder no longer looks random, so this isn't a good decomposition either. So we should choose a window that is more reasonable. This is the number of observations, so about 21 observations might be okay for this. You can experiment with different values until you get a smooth enough looking trend component, and the remainder should also look random. So you can see now in the trend component, there's small bumps, but it's mostly smooth, and the remainder looks pretty random. It doesn't have any trend or any cycles in it. So 21 is a reasonable value for the trend. The same goes for the seasonality. If I choose a very small seasonal window, perhaps 2, you can see how quickly my seasonality changes. It changes pretty much every year. Now, by definition, a seasonal pattern should be fairly consistent. Remember, it has the same pattern every year. So it's actually pretty common to choose a very large window for the seasonality. A large window will again prevent the seasonality from ever changing. And there's a special word we call this, periodic, meaning that it will never change. So this is also commonly used, but I think the default for seasonal windows is also good, which is 13. Having a window of about 13 seasonalities, 13 years in this case, allows the seasonality to change a little bit, because remember from the sub-series plot, it does change slightly over time. So step 4 that we've been doing now is choosing an appropriate seasonal window. And then step 5, use the decomposition. Make some plots. So of course we can auto-plot the data to see the result of our decomposition. There's a question from Amal. When do we need to adjust a decomposition? I assume you mean with these windows. Usually the defaults that we've set up in the package are pretty good. So often you'll just need to write STL of turnover or log of turnover if it's multiplicative. But if you find that the trend is not capturing all of the changes in the data, or maybe it's too smooth, then you should adjust the window to be larger or smaller so that it can capture all of the trend and cycles without bringing in the remainder. The same goes for the seasonality. If the seasonal pattern never changes, you should have a very large seasonal pattern, a seasonal window, such as periodic. If the seasonality changes quite quickly, you'll need a smaller seasonal window. Most of the time, though, the default windows are good. So again, with the decomposition, we can use this to more clearly see the seasonal pattern and the changes in the seasonal pattern as well, using the sub-series plot and seasonal plot that we saw yesterday. So in this case, it looks like the food retail is increasing for January and decreasing in February. I'll give you all of this code, and then I'm going to set you up with an example while we take a break. So I want you to look at the tourism data set that we saw last time. So we're going to look at the total number of people visiting Australia, no matter where they went or why they went. So try it yourself. Decompose the number of tourists to Australia. And I'll set you up with some code to get started. So step 1, transform if the data is multiplicative. You'll look at this plot and identify if it's additive or multiplicative and choose the appropriate transformation, log, box-cox, or maybe even doing nothing if it's already additive. Step 2, you'll need to do an STL decomposition. And I'll give you all of this code when I've finished writing it. Step 3, I want you to plot the decomposition and adjust the window if needed. Let me set you up a little bit more here. And step 4, explore the seasonality. So have a go with this one. I'll put all of that in the chat. And we're going to come back in 15 minutes. I'll be here, Bahman's here. If you have any questions, we can help you out as you work through these exercises. Try to find a suitable transformation if needed, a suitable decomposition for the data, so that you can more clearly see the seasonal pattern for this data set. I'll open it up to any questions. And there's one message in the chat about an error with geomline. Object turnover not found. I'm not sure how you would... I can see why you might get that. The variable that we're looking at here is trips. So if you look at the data set that we've set up, Austravel, you can see the columns of the data is quarter or trips. There's no column called turnover. That was from a different data set. So in order to plot the travel data, we will need to use autoplot of trips. And if you wanted to try a transformation, if you believe that this was multiplicative, you would use log of trips rather than log of turnover. I suspect that's where you're getting that error message. I'll also add, this one looks particularly difficult to find if it's additive or multiplicative. I gave you a tricky one. You can also use Guerrero's method. So you would use features, trips, Guerrero. This one's actually really interesting. If we've got a Guerrero's value of 2. Now, this I don't believe. This is one of the rare cases where it looks like Guerrero's method is not working. And that's because the way Guerrero's method is set up, if we look at the help file for this, which you can do with !Guerrero, the limits of values for lambda that it is allowed to choose is between -0.9 and +2. And the fact that it's chosen exactly 2 means that it wanted something even bigger than 2. So in this case, I think it's just an estimation failure of the algorithm. It wasn't able to find a suitable Guerrero's method. So I don't actually trust Guerrero's method for this data set. Don't trust because it says lambda equals 2. Personally, there's a lot of variation in this data set, so I personally think that this doesn't need a transformation. The STL model can handle quite a lot of changes in variation, as long as it's not systematic, like we saw in the previous example. I'll go back to that. If you recall from the food retail data set, it was very clearly multiplicative. In this case, we would need a transformation. But for a data set like the total trips to Australia, you can see it looks fairly consistent, the variability, about this big throughout the entire data set. Maybe it's a little bit smaller here when the value is a bit lower. So maybe like a square root transformation could work, but the STL decomposition would be able to work with this even without a transformation. So I would say we could try the square root of trips. Doesn't seem to have done much. Maybe we could try a log transformation. Yeah. And because the data isn't changing much when I apply the transformation, it's probably why Guerrero's method didn't work. It was trying to do very big transformations in order to make the data change. So in this case, data doesn't need any transformations. Daniel asked a question, is there any point to doing a decomposition before a transformation? So for an STL decomposition, it requires the data to be additive. So for the previous example on food turnover, where it was clearly multiplicative, if I did a decomposition without the log transformation, it would still work because the decomposition method STL is pretty robust. But you can see the seasonal component has that increasing shape. This is a bad transformation. This is pretty invalid. It's relying on the seasonal window to allow the seasonality to grow bigger over time. Whereas the relationship it's describing is additive, but the data is actually multiplicative. And so this decomposition is wrong. You would need to use a log transformation before doing the STL decomposition. So there's not really any, it's not sensible to do a decomposition without a transformation if your data is multiplicative. You need the data to be additive first in order to do the decomposition. Okay, so now that we've decided step 1, we don't need to do a transformation, the STL decomposition, we'll use trips here as the variable that we want to predict without any transformation. Now, did anyone choose a trend window and season window that you'd like to share? Enoch says 21 and 13. Let's try that. That's the same windows that I chose before. They tend to work pretty well. So if I plot that decomposition with trend window of 21 and seasonal window of 13, what do we think? I think it looks pretty good. You can see that the general shape going through the center of the data, I would want it to look like that. And sure enough, the trend component looks exactly like that line that I just drew through the center of the data. So the trend component, I'm pretty happy with. The seasonal component also looks fairly consistent. We can see the peak and the trough looking the same every year. There is a slight change in the shape of the seasonality. That's why our seasonal window of 13 being fairly small allows for changing seasonality. But importantly, it's not changing too much, and perhaps the seasonal pattern is getting a bit smaller towards the end. So that also looks good. Lastly, the remainder component also looks pretty random. In fact, it revealed to me something that I didn't see in the original data. You can see this drop here, a little outlier, is more obvious in the remainder term. And perhaps this increase as well for the trend change is more obvious in the remainder. So this STL decomposition allows me to more easily see the outliers and unusual effects and even the underlying trend by separating the components. There's some other suggestions to try a trend window of 7. Let's see what that looks like. So just switching the trend from 21 to 7. So in this case, now it's including that drop in the trend. And I would say this trend window of 7 is now too small because it's capturing a lot of the outliers, which should show up in the remainder. So because it's got lots of small bumps, it's reacting very quickly. I would prefer to see a larger trend window. Another useful way to remove the impact of outliers in the data is to set the robust option. Robust equals true. So if you set a comma in the STL function, robust equals true, you got to be very careful with your brackets here. This will remove the outliers from the estimation. It hasn't seemed to have fixed it up for the very small trend window, probably because this outlier isn't that extreme. So we should increase the trend window. A window of 17 looks pretty good. 21 also looks pretty similar. That all looks perfectly fine. Now, for our season plot, we want to do a season underscore year, a variable. We want to look at the seasonal component. And now we can more easily see the shape of the seasonal pattern. Whereas before, if we just looked at Oz retail, seeing all of the data, trips without any adjustment to the trend, removing it from the seasonality, you can see that the seasonal pattern is much more spread out. try that again. I'm not sure why it's not showing up. Oh, is it not called trips? Oh, this is supposed to be Oz Travel. Sorry. There we go. Here, it's very hard seasonality because it's changing a lot from, well, there's a lot of noise, I think, is the main problem here. A lot of random changes. But by doing a decomposition first, you can get a much cleaner view of what the seasonal pattern actually is. And we can see that the peak is in Q1, the trough, the minimum value, is in Q3. Whereas here, you'd have to really study it for a while to see that most of the bigger values are in Q1 and the lower values are in Q3. Okay, let's continue with the slides. Continuing on. One extra thing I wanted to show you with decomposition is that it also works for multiplicative, multiple seasonal patterns. It doesn't work for multiplicative, I misspoke. It needs an additive pattern, but you can have multiple seasonal patterns in the same time series, and it can separate all of them. So remember the electricity demand example we saw yesterday had a daily, weekly, and annual pattern. Here it separated the annual pattern of higher demand in winter and the higher demand in summer that is more variable because of heat waves, and the lower demands in winter and spring. And that repeats every year. So you can see that same seasonal shape repeating several times each year, or one time each year. You can also see the seasonal week component and the daily seasonal pattern as well. And these can change over time. Now, looking at a time plot of these, there's lots of weeks in 3 years. In fact, there's 160 odd, or 156. And there's even more days, almost 1,000 days in 3 years, or actually more than 1,000 days in 3 years. So there's a lot of data being plotted here. Using a season plot on this would make those patterns even clearer. Now, I wanted to finish this section on decomposition with a bit of a cautionary tale from the Australian Bureau of Statistics when they made a pretty big mistake and got in the news for all the wrong reasons. So this is back in 2014, a little more than 10 years ago. And the government was called in by the general public over the Australian Bureau of Statistics employment data. They made a big mistake saying that the employment rate increased by a large mark, much more than usual. And the ABS actually did a big change of actually giving up on their seasonal adjustment for this data set because they didn't know how to fix it. So hopefully this story will give you the skills to identify problems in your decomposition and prevent them from causing problems in the released figures, in the reports that you might write. And then lastly, the ABS, to try and fix up their decomposition, employed someone from my university, the professor that I work with, Rob Hindman, that makes the software with me, in order to figure out what went wrong with their decomposition and fix the methods for future years. So here's the data set. I think I can give you this. It's called employed, but it looks like this. We've got a very small seasonal pattern. Employment tends to be pretty stable. There's a little bit of seasonal employment for fruit picking during the spring season, and also retailers hire more people at Christmas to prepare for the holiday demand. Zooming in on the most recent years, you can see it looks pretty predictable. Here's my seasonal pattern, repeating every year. You can see there's this sharp increase in December for the holidays. Interestingly, it also appears to be there also appears to be a slight drop sometime in the middle of the year. It's an unusual pattern, for sure. If I look at a season plot for this, we can see that the trough appears to be in January, but it's pretty hard to see because the trend is spreading out the seasonal pattern. A seasonal decomposition, STL decomposition, would help us visualize this better. But there's one thing that looks particularly odd, and this is something that you should look for when you're looking at the original data. In the seasonal plot, are there some seasons that look very different from other ones? You can see in August, there appears to be a little drop in each year, except for 2014. In 2014, it appears to maybe even increase a little bit in August. There's definitely not a drop. And this is what caused all of the problems. When we calculate a basic difference, so this is similar to calculating a lag, and we focus on the difference between September and August, you can see that there's this big outlier when we do September values minus August values. And this outlier corresponds to the most recent year, 2014. Because usually for August, we saw that drop. So September is usually much larger than August. But in the most recent year, we saw that it was pretty similar. Maybe even August was larger than September. So August, September. So the difference for 2014 alone is actually negative, whereas normally it's several thousand people more employed in September. So this difference freaked a few people out, and it made a pretty big change to the economy and the stock market. The reason why is because the ABS usually reports seasonally adjusted data. So they look at what's common for the seasonality and then subtract the seasonality from the original data. And usually what they're subtracting is a big drop in August. So when you subtract a small value, you're going to increase it overall. So what the data that they actually published looked like was this. Fairly stable, smooth data, a little bit of random variation that was coming from the remainder term. And then this caused all of the news. This big, sharp increase that happened in August 2014. Now, this increase is unlike any other change in the past that we've seen for 20, 30 years, all of time on record for this data set. And then they also reported a big drop in September, whereas normally September increases the amount of employment. So something drastic seemingly happened to how people employ in August and September. But upon further investigation, this pattern is not actually real at all. There is no drop in employment in August. There's no increase in September. What was actually happening is that the ABS asked an extra survey in August, and they only asked this survey if you said, yes, I'm employed. So what lots of people were doing was lying. They were saying, only in August, oh, I'm not employed, I lost my job, because these people knew that they would be asked more questions if they were saying that they're employed. So they wanted to save some time. They didn't want to be asked these extra questions. So that's why we had usually in the past a drop in employment records in August, which was completely artificial. It was only because the ABS was asking this additional survey. Except in 2014, why 2014 was no different, was very different, is that they chose not to run the supplementary survey. It was not run. And so no one lied anymore. And they actually answered truthfully that, yes, I am employed. And so employment figures for August was much higher than usual. And that was made even worse because the seasonal adjustment, which usually expects seasonality, the August employment to be lower, when we removed that seasonality, subtracting it, increased the employment even more. And so this was a big stuff up and a big mistake from the ABS that caused a lot of problems, largely because they made people work more for answering the questions in a certain way. And people understood that and were not answering truthfully. So now there's a new method that was introduced to adjust for this bias caused by the supplementary survey. And when we talked yesterday about additional predictors that you might use in the model, here we might use a predictor for employment of if we ask them additional questions with the survey. That would be one easy way to fix this problem in a regression model, for example. Okay, that's all I had on decomposition. I want to open it up to questions in general about decomposition before we move on to the next topic, which is how we can use decomposition to visualize the trend and seasonality in hundreds of time series. Because so far we've only looked at time series, individual time series, or maybe up to 8 time series at once that we saw at the end of yesterday. But often, like in the tourism data set, what we actually have is hundreds of time series. You can see tourism has 304 different time series, which will be very hard for us to plot all of them at once. So before I move on, I want to open it up to any questions about SGL decomposition. Let me know if you have any questions about how you can use decomposition, why you might use it, and how it helps you explore data. There is one question, where is the employed dataset? I believe you can find this on the GitHub page for the website. If we go to materials, which has all of the code that we use to make the slides, you can see we're using QMD documents to create these slides. Then if you go to the data folder, maybe it's not there. Let's have a look at adjusting and transformations. Okay, so here's the data. It's included in the code itself. It's not published anywhere as a CSV. So I'll send you this line of code. Oops, not the code, the link to the code. So that's how you can get access to this data set if you wanted to use it as an example elsewhere. Okay, there's another question. A lot of examples have used financial data, such as employment. How can we use decomposition for health data? It's a good question. It works exactly the same. So if I looked at, say, the PBS data set, this is the number of medications distributed in Australia, subsidized. And I wanted to compute the total number of medications subsidized. I'll call this PBS total. You can see that this has a seasonal pattern. It looks fairly hard to tell. Let's try it looks somewhat additive, somewhat multiplicative. It's not changing very much, at least. This variation appears slightly smaller than that one. So maybe a log transformation would be good for this. Let's try a square root. Yeah, with a square root transformation, it looks stable. We could also look at Guerrero's method, and it says 0.6 is optimal. So a square root being 0.5 is very good. We could then estimate an STL model with the square root of scripts. I'll just leave it as default. Extract the components and plot them. And there you can see we have a decomposition of the trend and seasonality and remainder from the PBS dataset, which we could also use to more easily see the seasonality in the seasonal component without having the trend in the way. So now it's much easier to see that the minimum number of scripts happens in February and the maximum happens in December. The reason why February probably has a lot less is there's less days in February. And I think also the benefits, there's a subsidy that gets smaller in February, depending on how many medication you need. I believe also, I can put this code in the chat too. All of this code will be put on the website at the end of the day. So you can, regardless of what data set it is, if it's for financial data, medical data, transportation data, environmental data, you can use the exact same method, STL decomposition, to separate trend and seasonality. There's another question, how can I find the optimal value of trend and seasonality? Unfortunately, there's no method like Guerrero to automatically find the best values of trend and seasonality. Fortunately, the choice of the window isn't very sensitive. So as long as you're close enough, it will work just fine. One way that you can find the best value, I believe, is to use cross-validation. Can you do that? Let me check really quickly. Can we glance this? No, we can't. No, unfortunately, I don't know of any good ways to identify the best trend and seasonality besides looking at the plot. Maybe Bahman, do you know any good methods for automatically identifying windows? Or any statistical tests for how good a decomposition is?
No, Mitch, I'm not aware of any actually.
Well, I've just found that I'm not, sorry, I can't hear anyone. Okay, I could hear that. Bahman, I couldn't hear you though. It looked like you were talking. No, I still can't hear you, Bahman. Perhaps you could change your microphone.
Second.
That's better. I can hear you now.
All right, now can you hear me now?
Yes, I can.
Yeah, no, I'm not aware of any statistical test for this. Well, in my own work, to be honest, I trust the algorithm most of the time. I don't bother a lot with finding the best, let's say, parameter or whatever. When it comes to
that's very similar to what I do. I'm not aware of any optimal process for finding these windows. It'd be an interesting research direction if anyone wanted to try to come up with a method to find what is the best decomposition?
Yeah, just I mean following that because there was there are a couple of questions and we had it before as well about using it for different applications. So Mish explained it, but what I also suggest you to do is basically take the code that we provide and now replace things with your own data set, starting from reading your own data, identify what are the variables or columns in your data, and then try to replicate, what we have done here, but with your own data. I think this is basically the best way to go forward and learn more and also do something that is useful for your own work.
I agree completely. And with the exercises that you'll do in the afternoon, you're going to do exactly that. So we've got these methods, and you can try that out on a new data set on your own. And we've also got the exercises, the apply exercises, which is a much more realistic example with a medical background as well. So this is about doses of vaccines and the amount administered. And your task for today with your mentors is to perform a decomposition on that data. Another question from Amal: if it's hard to visually identify if the time series data is additive or multiplicative, what can I do? Usually, if it is hard to tell if it's additive or multiplicative, the model will work just fine without a transformation. So I would default to avoiding a transformation unless you can clearly see that it is multiplicative. If it is additive, or if you're not sure, it's usually better not to transform the data. Okay, I think we've gone through all the questions now, so it's time to move on to the next session. This session's a little bit shorter. It's about computing and visualizing features. So I'll put the link to this as well. For you all to follow along. Give this a moment to load. Okay, computing and visualizing features. You can see that this really builds on top of the STL decomposition that we've just done. Because STL, the way that it separates the trend and the seasonality, is actually really useful for summarizing a time series into how strong the trend and how strong the seasonality is. And quite often what we want to compare between several time series is its patterns. Does this time series have trend? How much trend does it have? Does this one have seasonality, or is this one non-seasonal? And there's a couple of statistics that we can compute from a decomposition. So in the first box here, this is what we just learned about in the previous session, how we can use an STL decomposition to split up the data YT into its patterns of trend, seasonality, and remainder. And then once we've done that decomposition, we can reuse the seasonality and the remainder in order to calculate the strength of the seasonality. We do this by calculating the ratio of the variances. The variance of the unexplained bits divided by the variance of the seasonal plus unexplained bits will give us the strength of the seasonality. So if our random bits is very small and our seasonality has a very high variance, then this ratio will be approximately equal to 0. So 1 minus 0 will be equal to 1. So having a high seasonal variation and a low random variation will give us a strong seasonal strength, close to 1. Let's also imagine the opposite of this. If I had a very large random variation and a very small seasonal variation, my seasonal variation plus my random variation will be roughly the same. So this is approximately equal to 1. And so 1 minus 1 will be equal to 0. And this tells us that my seasonal variation, seasonal strength, I should say, is close to 0. So very weak seasonality. You can apply the same idea to the trend. If the trend variation is very large and the random variation is very small, my trend strength will be close to 1. A 1 indicates a very strong trend compared to the randomness that exists in the time series. The way that we compute these statistics is actually very similar to how we computed Guerrero's method. We again use the features function, but instead of using Guerrero, we use feat STL. Feat is for features, STL is for STL decomposition. And this will compute the strength of the trend for the time series, the strength of the seasonality for the time series, and also a few other statistics like when the peak is, when the trough is, how spiky the data is, which is roughly the randomness component, how linear the data is. There's all sorts of things that we can look at based on an STL decomposition. But usually what we're most interested in is the trend strength and the seasonal strength. So I want you to try this out for yourself. Let's go into R. Let's have a look at tourism. If I tried to plot all of the data from the tourism dataset, I'll need to remove the guide because otherwise there's just going to be too many time series to plot. You can see that we just get a lot of ink on the page. I can't see any of the patterns in any of the time series here because there's simply too much data to plot using time series plots. So instead, it's a good idea to compute summaries of each time series. And a summary of a time series is called a feature. We can, for instance, calculate the optimal transformation, Guerrero's method, for every time series. And this will tell us how multiplicative a time series is. So you can see holiday travel to Adelaide is very multiplicative because the transformation, lambda, is very far away from 1. Whereas the visiting travelers to Adelaide has a lambda of roughly 0.9, very close to 1. So this time series is not very multiplicative. Let's see that. Let's filter out region equals Adelaide and purpose equals holiday. Let me make that look a little bit more familiar. There we go. Okay, that's not a very good example, I think. What's happening here is that when the values are lower, which is this part here, the variation is small. And when the values are larger, the variation is bigger. So that's why it's needing to do a log transformation, but that's not very clear. So in this case, I think it's also not too important to do a transformation. There's other time series when it would be more obvious. Let's try visiting. Yeah, here the data, regardless of where you are, so the lower values have the same variation as the bigger values. So this one is additive. But Guerrero's method is one of the interesting ones. More interesting is the features from an STL decomposition. So I'll share this with everybody. I want you to try this out. So if you compute the features from an STL decomposition, for each of these time series, it's computed the strength of the trend and the strength of the seasonality. So I want you to tell me, try to use filter. No, let's try to use arrange. Arrange is a function that sorts the data based on one of the columns. So I can look at the trend strength. Sorting it by trend strength will tell me what is the least trendy time series, the time series that has the least trend. So that is east coast of Tasmania with the purpose of other. And if I look at that time series, you can see there's no trend in this time series whatsoever. We can also look at the most trendy time series by sorting the data in descending order. So the time series that has the most trend is Australia's Northwest for business travel. I think that's Northwest. Let's check that. Give it a bit more space. Hold on. Yes, Australia's Northwest has the strongest trend for business trips. Let's see what that looks like. You can see that this time series has a lot of trend for this data set. It's increasing the most. I want you to try to change this code that I've just put into the chat. Tell me what is the most seasonal time series in the tourism data. So you'll need to adjust the column that we're sorting the data by to reveal what is the most seasonal time series. And when you figured it out, put it into the chat. So we found the least trendy time series by sorting in order of trend strength. So this is ascending order. So it'll start with the smallest trend time series and then the biggest trend time series. Sorting it in descending order will reveal the biggest to the smallest. So to find, it looks like someone's got the right answer. To find the most seasonal time series, we'll want to sort in descending order of season, strength, year. Sorry, what was it? Season. I've mistyped the column that we're looking at. Is it seasonal strength? Yes, it is. Seasonal strength, year. So now you can see almost all of the seasonal time series are holidays. People only travel when the weather is good. So that's why it's very seasonal demand. And the Snowy Mountains in New South Wales is the most seasonal time series, closely followed by the Great Ocean Road in Victoria. So you can see these seasonal strengths are very close to 1, which is perfect seasonality. Let's have a look at the Snowy Mountains. for holiday purpose. And if you ever wanted a perfect example of seasonal data, this would be it. You can see a very strong variation in the seasonal pattern, not much remainder, not much randomness going on. It's purely seasonal. So the features, especially STL features, allow you to summarize a large collection of time series with just single numbers. If I asked you to find what is the most seasonal time series and I just gave you the tourism data set, you would have a very hard time searching through each of these time series, plotting them, and trying to visually see which one is more seasonal than the other. Being able to calculate summary statistics or features from each series makes this possible. The other really cool thing that this allows you to do is to plot the features. So if I use ggplot directly, and I'll put the code into the chat if you're unfamiliar with ggplot, and I'm going to put the strength of the trend on the x-axis and the strength of the seasonality on the y-axis, and then make a scatter plot. We no longer have time to worry about, so I can do any sort of cross-sectional plots. Now we can get an idea of all of the time series in a single plot. So there's a few time series that are very seasonal. There's not many time series that are very trended, right? The trend generally isn't as strong in these time series, but the vast majority of my time series don't really have much trend or seasonality in them. So with this, we can identify some of the models that we'd use for different time series. The models that have a lot of seasonality, we would want to include a seasonal component in the model. This model down here, this data set down here, doesn't really have anything in it. No trend, no seasonality. So we would need to use a very simple model to capture that data set. What's more interesting is if we set the color of these to be the reason for why they went on that trip. So if I color each of these points by purpose, have a look at all these ones at the top. All of the very seasonal ones are for the holiday purpose. Whereas business travel, in red, tends to happen mostly down here, where it's not very seasonal at all. People just have to travel for work no matter what the weather is. Whereas if they're visiting friends and relatives, this is a little bit more seasonal because people choose to travel for holiday periods, perhaps at the end of the year. So there's lots of ways that you can visualize this. Here's one way. We've added an extra faceting step to this so that we can see each of the states of Australia separately. Looking at this, which state appears to have the time series with the strongest trend? So the trend is on the x-axis. So ACT has pretty average trend around 0.5, maybe a little bit lower. Which of these time series has the most seasonal, most trended patterns? So it has most of the points towards the right. Yes, looks like everyone's getting the answer now. So Western Australia, all of the time series here generally have trend strengths larger than 0.5. Some of them are close to 1. Whereas every other state doesn't have any trended time series like that. Maybe some locations in Victoria are also pretty trendy. So here we can interpret that Western Australia has the strongest trends. And if we looked a little bit closer, maybe calculated the coefficients, we would see that generally there's more people traveling to Western Australia. The trend is increasing. What about seasonality? Which of the states has the least seasonality? So remember, seasonality is on the vertical axis. Which of these states has the least seasonality? Very good, everyone's getting the right answer. ACT, there is only one region in ACT called Canberra, and it has very little seasonality, no matter why they're traveling. Every purpose has very little seasonality. It's all less than 0.5. And that's because this is where all the government is, and there's not really any tourist attractions or anything interesting going on there that people might like to travel at certain times of the year for. Whereas New South Wales has lovely beaches like Byron Bay and Bondi Beach. So a lot of people want to travel there in summer. Victoria has a few ski slopes for winter. And Tasmania, it's way too cold to be there anytime except summer. So a lot of people travel there only at certain times of the year. So Western Australia has the strongest trend, ACT has the weakest seasonality, and we can also see all of the blue dots appear to be right at the top. So holiday travel is more seasonal than other reasons of travel. Now, previously we calculated the most seasonal time series by sorting the data. You could also use the filter function to do this. Here I'm finding whatever row is equal to the maximum seasonal strength. And sure enough, we find the Snowy Mountains holiday purpose is the most seasonal. Now this code is a little bit fancier than what we did earlier. What we're doing is a right join, which keeps only the rows of tourism, only the time series that match the key variables, state, region, and purpose of the data set containing only the most seasonal values. So I'll go through that again a bit slower. This code is slightly better than what we did before. In fact, I'll show you this in R. This code, I'll put it in the chat box for you as well. So what this code is doing is calculating the features for all of the time series, all 304 different time series, trend strength, seasonal strength, 304 rows. And then we're keeping only the row that has the maximum seasonal strength. So filter, strength of the seasonality equal to the maximum seasonal strength. And that gives me one row of data, Snowy Mountains holiday travel. I'm going to save that as most seasonal. And then this right join function is a very nice function to learn, because what this does is keeps only the rows of tourism that match up with the values in most seasonal. So Adelaide for business travel in South Australia is not matching any of the time series here. So it's going to be removed by this right join. All the other time series except Snowy Mountains holiday travel will be removed. And then I can simply plot that data set like so. Another way of doing this is to use slice max. So sorting by seasonal strength year with the slice max function, I can actually extract not the most seasonal, but the top 5 or the top 10, however many I choose to extract. So this is from the tidyverse, and it's a useful one to learn. There's also slice min if you wanted to look at the least seasonal. And if I do the right join for this, it saves me from having to write the filter for region, Snowy Mountains, holiday, Great Ocean Road, holiday, South Coast, holiday, all of these one by one. I can use a right join, which will keep only those 5 time series that we're interested in. So plotting this, I've now got a plot of the top 5 most seasonal time series. So if you're just interested in the most extreme time series, this bit of code is a useful one to keep. And of course, this will be included on the website at the end of the day. So we also saw how to calculate the maximum trend, and we got the correct answer before, Northwest Business Travel. I want you to try and adjust the code that I've just sent you to instead plot the top 5 trended time series. So you'll need to replace the name of the dataset that you'll be right joining and the column that we're slicing. Try to create a plot of the most trendy time series. So the main thing to change here is instead of slicing the most seasonal time series, we want to sort by trend strength. And this will give us the time series that all have the 5 strongest trends. So you can see these are generally in Western Australia and Victoria, the 2 trendy states that we saw earlier with this plot. You can see it's picked out these 2, and I think this one as well are the 5 time series that we're looking at. And if we give this a name, so maybe top 5 trends, and plot all of those, you can see that these generally have a lot of trend, right? Very strong trends. Now it looks like this one looks fairly flat, but what's happening here is the scale of each of these plots are all the same. Right? See how it all ranges from 0 to 800? The statistic for trend strength is independent of scale. So if I modify this plot code just a little bit to ignore the scale or free up the y-axis, scale equals free y-axis, then I'll have different y-axes for each of these plots. So the first one is 0 to 800. The next one is 0 to 200, it seems. 300 to 800, it looks like on the first plot. But you can see each of these have quite a strong trend. And the most trendy, I believe, was this one, Northwest. Looks pretty strong. I would say the holiday travel to Melbourne is also very strong. Okay, do we have any questions about the strength of the trend and the strength of the seasonality? We've got heaps of time for questions today. We might finish a little bit early. Just wanted to check how we're going before I move on to different types of features from other statistics that we might like to use. Okay, one question. What if the trend is strongly decreasing? How would the trend strength turn up? That's a good question. So what if I had, let's see, so this data set has a lot of trend. Very clearly increasing. If I calculated the STL features of this data set, sorry, it's feet STL, you can see my trend strength is almost exactly 1. And my seasonal strength is also close to 1. This is a very strong trend and very strong seasonality, about as strong as it gets. What we don't get here is an indication of if it's a positive trend or negative trend. That would be a good one to add. If I instead calculated negative turnover, now I've got something that looks like it has a decreasing trend. So if I calculate the features for this negative trend, you'll see it makes absolutely no difference to the strength of the trend. That's because this statistic is based on the variances of the data rather than the shape of the data. There's some other statistics that you could compute for this. You could do a regression model and calculate the trend slope, for example. I'm not sure if we have a specific feature for this. Not that I can think of. That would be a good one to add. But you could write that yourself. You could probably say calculate trend. This is a bit advanced, so if you're not familiar with writing R functions, don't worry about it. But a quick way to estimate the trend would be a linear model of x against sequence along x. I think that will do it. Yes, that looks like it works. So one of the nice things with the features function is if there wasn't a feature that did something that you needed, you can write your own function, create a new feature for estimating the trend slope, for example. And then I could use this feature inside the features function. And you can see I get my negative slope for this data set. But if it was positive, like it is in the actual data, this one, I get my positive slope. So you can create your own features based on statistics of the trend. Anything that gives you a single number as a result can be used as a feature. Yes, I will send you all these functions. The idea of this is more to illustrate what can be done with features and the general idea that they are just statistics that summarize time series into a single value. And what I've just done here is quite advanced. So it might take some time for you to read through and understand. And most of the time, all that we would use is feat STL to look at the strength of the trend and seasonality, because the direction of the trend is less important for choosing an appropriate model. It's more the presence of trend or seasonality that is important to help us understand or identify what models we need to use, models that have trend or don't have trend. Okay, I think there was another question. No, I think I've covered everything. Okay, so in the previous yesterday, when we looked at visualizing data, we also looked at ACF plots. So let's see that as well. Remember how we produced these plots of the ACF? And this slow decay, all the positive values indicated that we had trend. And the spikes that happen at multiples of 12 in this example indicate seasonality. Now, this can also be used as a feature, because if I look at the ACFs, the lag 1 ACF is a one-number summary of the time series. The lag 12 ACF, that's not shown here, but it's a bit stronger, this one here, is also an indication, a one-value summary of the time series. So another useful feature that we often use is ACF features, which we can use feat ACF to compute. And here you can see we get the strength of the first order correlation, 0.96, is exactly that value, 0.96, from the usual way that would compute the ACF. The 10th ACF is also usually interesting. We've also got the differenced data. I'm not sure why this is 8.5. That might be a bug. I'll have to look into that later. But what we'll see in a couple of days' time when we look at ARIMA models, it's also useful to difference the data and then look at the order correlations from that. We can also see the strength of the seasonal order correlations, 0.922, is exactly this value, 0.92. So what you'll end up doing quite often is combining many different features together. We could compute the STL features and the ACF features all in the same table. So now I've got 16 different features. I've got my trend and seasonal strength, but I've also got all of my ACF features. And in fact, the feast package includes a whole lot of features. I think we could add some more, but there's about 50 features in the package that you can compute. And you can calculate all of them with features all. No, sorry. Feature set, I think it was. Yes. So that's computed all of the features that are loaded in all of the packages that we have. So this is loaded in 48 different features. And you can see there's Lambda Guerrero that we're looking at before. There's KPSS tests, there's Phillips-Perron tests, PACFs, all sorts of interesting features. We're not going to go into the details of what each of them are, but they are useful for separately identifying time series. And what this allows you to do is dimension reduction and clustering to find related time series, ones that have similar appearance. Has anyone done, maybe we could have a show of hands on Zoom. Has anyone done dimension reduction techniques before, such as PCA? So we should be able to use the React button to raise your hand. So these dimension reduction techniques are similar to t-SNE, PCA. There's a few different methods for this, but they are unrelated to time series. They're used for cross-sectional examples. You can probably use them for time series data as well, but almost always they're used for cross-sectional data. So it looks like there's not that many people that have used PCA before, so I'll take it a little bit slow. But the idea here is that we will compute all of the features from the feast package, all of the features that we have available to us, which in this case looks like there's 51 for region, including region, state, and purpose, the key variables. So there's actually 48 different features. I'll copy this one for you as well. So this will take a little while to run because some of the features involve estimating models like STL decompositions. And it is estimating those models and computing those features for all 304 time series that exists inside the tourism dataset. Just make sure I'm saving that as a result. So that's why we're saving it as tourism features, so that we only need to compute it once and we'll reuse them for our plots and our dimension reduction later. Okay, it looks like that might take a little while because my computer's, just of course, as soon as I start talking about it, it's done. So if your computer is a bit old like mine is, it might take a while to run these. But you can see we have a whole collection of different features available to us that we could look at, and 304 for all 304 time series that exists in the dataset. What I can do with this is use the PRComp function to extract principal components. So this function is built into R. And the way it works is that if you have a set of numerical variables in a data set, so that's why we have to remove our key variables, region, state, and purpose. So now our data is like so, just the features without any identifiers for them. Then I can use the PRComp function, which is built into R, to perform PCA, Principal Component Analysis. And what PCA does is that it adjusts the data across multiple columns so that we create new variables that are linear combinations of the others in a way that we maximize the variation. So rather than having a column called trend strength, which contains the trend, we now have a column called PC1. And PC1 contains principal component 1 that is the most variation explained possible in a single column, at least using linear combinations of these features. It's a linear transformation. PC2 is the second most explanatory variable combination that's possible, and so on. And I believe if we plot this, there's a way to plot your principal components. You can see after the first two principal components, almost all of the variation in the data is explained. So it drops off very quickly to say that after two variables, you don't really need any more to compare the time series. If you used 3, 4, 5, 6, if you use 6 principal components, then you're explaining a lot of the variation in the data. But after this, it's starting to get pretty flat and not explaining much of the information. So even though we've got, what was it, 50 series, 50 different features in the data? Yeah, 51 columns, 3 of them are key variables. So 48 different variables. Only 2 variables are needed to explain most of the variation. But the tricky part is finding out which ones, or how to construct those 2 very interesting variables. Because these 2 variables are actually combinations of all 48 different features. So on their own, they're mostly meaningless. But the nice, useful thing that you can do with this is to identify clusters. So the next step that I've added here, the augment function, is adding these principal components, 1, 2, 3, 4, etc., back on top of my original tourism features dataset. So now instead of 51 columns, I have 100 columns. The additional columns are my principal components columns. So I've got dot fitted, PC1, PC2, PC3, etc. Now, which one of these principal component columns are interesting to look at? The first ones. Principal components 1 and 2 are the most interesting because they explain most of the variation in the data. So what I could do is put on the x-axis principal component 1, on the y-axis principal components 2. And just like I did before for plotting seasonality and trend, I can do a scatter plot of those 2. And with this, I can see, well, this time series is very weird. This time series is unlike any other. These time series are pretty common. They look like every other time series in the dataset. There are some time series which are similar to each other, but not most of them, right? There's some that have a stronger trend or a stronger seasonality, perhaps. But we don't know what this cluster up here represents, nor do we know what cluster this represents. What we can do is filter the time series to explore that. We could also color by some of the categorical variables like purpose. And this reveals to us that the holidays have much higher principal component 2, which likely suggests that principal components 2 is largely related to seasonality. And I'm guessing that principal components 1 is largely related to trend. So that's what I've just done now. We've got our principal components plotted, PC1, PC2. The downside of plotting principal components is that they're less intuitive, right? They don't explain as much because they're no longer attached to things like trend and seasonality that we understand. This is some linear combination of everything: trend, seasonality, kurtosis, Guerrero's lambda. Every method has been combined to compute PC1 and PC2. What it is useful for is identifying the outliers. If I plot by state, I'm not seeing much structure. If I plot by purpose, you can see the tourism travel, the holiday travel is at the top. And our outliers, the ones that are really weird, seem to all have values of PC1 greater than 10. So one thing we can do with this is now plot the outliers. What time series look absolutely unique? We have a new feature that we could use, not trend strength, not seasonal strength, but principal components to spot the outliers. So just like I did before, I'm going to copy from above. Just like when I computed features and used slice max to find the most trend and most seasonal time series, I can also use principal components what would this be? Tourism features. I can also use principal components to find the outliers where principal component 1 is greater than 10, right? Because from the plot, we saw that this line is a good way to find the really weird observations. So if I keep only those rows for those 4 observations, so I'll call this tourism outliers. Sorry, this should be PCS, the one that I've computed the principal components on. We can see that the weirdest time series is Melbourne holiday travel. That's probably weird because it was very strongly trended. Western Australia's northwest and southwest for business and holiday, also having very high trend, one of them having very high seasonality as well. I'm guessing that that's this one up the top. We have 4 very unusual time series, which we can use the same code as before to plot them. So this one is probably very weird because it's very seasonal. This one is weird because it's very trended. This one also very trended. So we have the most extreme time series that exist in the dataset by using clustering and principal components to identify the outliers. And there we have that same plot. That's all I have for slides for today. We have about 15 minutes left for questions, if you have any. I realize that that was a lot, and it's really useful techniques to use if you're working with large collections of time series. If you've got more than 10 time series, it's very hard to plot them using a time plot or a seasonal plot. So the best approach for this is to use features, especially the STL features that we started with. I usually just look at the trend strength and the seasonal strength to get an idea of the patterns across all of the time series in my dataset. I do also want to mention that tomorrow you do not want to miss, because tomorrow we'll be producing our first forecasts. And in fact, for the rest of the week, it'll all be about how do we produce forecasts from some basic methods tomorrow, including regression for using extra information. And day 4, we'll look at some of its more advanced statistical methods of ARIMA and ETS, which tend to work very well for most time series. And then on day 5, we'll learn about how to evaluate our forecasts to choose the best model using accuracy statistics and checking the assumptions of the models with residual diagnostics. So I know today was a little bit different, a little bit advanced, but you don't want to miss tomorrow because we're going to start producing our forecasts. Okay, I'll be here for some questions if you've got any. The exercises, of course, you can work through independently and with your mentors. And for those that want to leave now, I look forward to seeing you all tomorrow to make some forecasts together. Let me know if you've got any questions. Oh, I will also add, the recordings from yesterday are also on the website now. If you go to the schedule for day 1, down to resources, you'll be able to find the recording from yesterday, AFRICAST Day 1, 2025. And you can also download the code from the exercises yesterday. So I'll put this link in the chat as well. If you're curious, you can also watch the recordings from previous years as well. So we have every past AFRICAST on the website.
Hi, Mitch. Please, I have a
Hello.
question. Probably because my background is more with like longitudinal data. So when you were talking about using the PCA and that plot you displayed, I'm trying to understand those extreme 4 values. So I think basically what I'm struggling with is things around trend and then seasonality, the distinction, and also could it, and when you say something like, I think in your SIBO, where you have the number of dimensions and it has something that describes the time. Is it like saying, for example, in a longitudinal data, will that be that you, for example, have a specific measurement collected over, let's say, 12 years, and your time variable is annual years? So will that then be the 12 there? I don't know. Probably I'm not asking my question appropriately, but I think I'm confused about those
No, not at all. It's
extreme
very clear.
values there. Okay.
No, it's very clear. With longitudinal data, you can use Sybil as well. Usually longitudinal or panel data doesn't have much time information in it. Like you described that you've got 12 years of data, or data across 12 years, maybe observed every few years. And often with panel data or longitudinal, you've got a lot more people, a lot more individual time series within it. So the way you would set that up is, imagine we've got some panel data. In fact, I might have panel data built in. Chick weights, I think. What was this data set? Okay, let's see if we can convert this into a data frame. Okay, so this is a type of panel data. It's a little bit different. Here we have an identifier for a chicken, a baby chick. And here we have our first chicken. And then we've got a time variable, which is the number of days since the chicken hatched out of the egg. So on the 0th day, it weighed 42 grams. On the 2nd day, it weighed 51 grams. And I can convert this into a Sybil. The index variable is going to be chick. And the index variable is going to be time. And my key variable will be chick. So here you can see we've got 50 different chickens in this data set, and the time interval is 1. And in a panel data set where you might have people, you would have your key variable being the identifier for each person, and your year column, which has annual observations over 12 years, would be your time index. Now, you usually can visualize panel data with a time plot because there's less data to show. But if you've got thousands of people to show, it's probably not going to work for a time plot. Instead, you can compute time series features, just like we've done today, to calculate maybe the growth rate of the chickens. Or if you've got longitudinal data on kids, you might want to measure their height as they develop. And then you can see areas where children are growing taller quickly, and maybe children that have stunted growth as well. So that would be using a feature such as the trend feature that we created, or using trend strength from the STL decomposition. The use of principal components could be useful even without features. If your time series, your panel data, measures lots of different features, so maybe a person's height, their weight, their income, their savings, their number of friends, the amount of medication they take. You could imagine lots of different variables that you might collect in a panel data set. You can then use principal components on those variables to reduce them into just 1 or 2, which you can then use to detect outliers or perhaps mistakes in the data. So all of these methods can also be used with panel data. It's very useful when you've got a lot of different columns or a lot of different features from the data. That's a very good question. Thank you. There's another question by Ali. At the end of the lecture, can we get the scripts? Yes, you can get the scripts from the website. So again, if you go to the schedule, down to resources, you can download the code by clicking on this button here. I will need to update this one for today's code and yesterday's code, but that will be ready in a few hours. Okay, we have a couple more couple more minutes for questions. I'm just looking through the exercises that you'll do this afternoon. Perhaps most useful would be recapping the transformations for when you're doing the log transformations or Box-Cox transformations. There's a different example here, which is the number of sales in Victoria for cafes, in which you find Guerrero's method. So this code will step you through the process bit by bit and allow you to copy the code and try it for yourself in R. And then there's some exercises for finding what the best box-Cox transformation is for the total retail turnover, rather than just the turnover for Victorian cafes. So instead of filter, you'll need to think about how to compute the total using the summarize function. And then for decomposition, we're using a different example here with Australian print. And notice that this is a multiplicative time series. So we need to find a suitable transformation before we do the STL decomposition. We separate the components, and then it's easier for us to look at the seasonal pattern. So try to produce a season plot with and without a decomposition. Then lastly, using features, we can summarize the strength of the trend and seasonality for retail sales and find that there's most of the time series are very trendy and very seasonal, but there's some that have slightly less trend and some that are not seasonal at all. And then lastly, you'll apply these same ideas, but for doses of vaccines in Africa, using the exercises project that we set up yesterday. Looks like we have one last question. Why do I need to use principal components? So principal components are useful for summarizing information across many variables. Remember from when we computed the features, tourism features, we had 48 different numerical variables that we might like to look at. So we had trend strength, seasonal strength, we've got the ACFs, PACFs, zero means, etc., linearity. We can't look at all of this at once. So principal components is a technique of combining all of these variables, all of these extra features that we can't see into one or two different most relevant components. You saw the variance where the first two principal components had very high variation. What that says is that all of these 48 columns can be summarized into essentially two different variables, PC1 and PC2. And that is the best way to separate each of the time series so that we can identify which time series don't look like any other time series. So principal components is a pretty advanced technique, and it's most useful for clustering similar groups of time series and also finding time series that don't look like any other time series in the collection. So it's a way of finding groups of similar patterns and also individual series that are completely unusual. Okay, that's all we have time for the sessions today. I hope that you enjoy the exercises. If you found this a bit confusing, the exercises do go into a lot of explanatory detail for each of the steps. So you can skip through to the bits that you were a bit confused on and want to go through in your own time. And then I hope with your mentors this evening, you can try to work through the vaccine dosages and see how you can apply these techniques on a real example data set from Africa. You don't want to miss tomorrow because that's when we'll look at producing our forecasts for the very first time. I hope to see you all then. Thank you all very much. I'll stop the recording here.